processing for most of the applications are very fixed cochlear models, and they don't vary in characteristics. So let me just move on to the next slide. So my talk will be just introduction to a human auditory system, basic introduction, then models of the cochlear, and then how to adapt the model, how to change the model, adaptive models. Then I'll just concentrate on integration of the cochlear models with machine learning. Just a small part. So let's look at the first slide. So let's look at the peripheral auditory system. Peripheral is divided into three parts: middle ear, outer ear, middle ear, and inner ear. So you can see here from the diagram, that's the outer ear part, middle ear, and the inner ear. Inner ear is the important one, which is the spectrum analyzer. So the outer ear is a simple resonator. We'll look at that in a minute. And then the middle ear is an impedance matching, because you've got a vibration, and then you're going to transmit that to the inner ear. And then inner ear would be the spectrum analyzer, actually analyzing the signal, And the bandwidth of the signals, the human ear can respond from 20 hertz to 20 kilohertz. It can go slightly 21, 22, but there's no hard and fast rule as exactly 20, okay? And just to give you a little bit of feel for the sound and the intensity, for a normal moderate conversation, it's just a conversation that I have with you, just general conversation, it's around 60 dB. I mean, 40 dB to 60 dB is the normal general conversation sound level. Anything below that is a lower level faint. And if you go 80 dB is very loud, or you could say loud, and 90 dB is very loud. And when you go 120 dB, it's very, very loud. So you tend to use your hand to close your ear. Otherwise, you will damage your system. So the comfortable range is around that. But Cochlear can handle around 120 dB, from 0 dB to 120 dB. You can still don't need to close your ear with when you're at 120 dB. It is painful after some time. But if you go any intensity, you probably will damage your ear. So it's very important that you have to protect your ear if you're working in a very high intensity sound levels. Let's move on. So I'm now going to go one at a time. Outer ear, which is a resonator. What do you mean by a resonator? So if you look at the outer ear, and I've done the calculation here just to show you, it has got a resonant frequency around 3 kilohertz. So about 20 dB gain it provides them. So it's a broad bandpass filter. It's actually this length is it's kind of a resonant tube. It's a broad bandpass filter, and it's about at 3 kilohertz. It gives you about 20 dB amplification. That's all it does externally here, but it makes sure it directs the sound through this one and to eardrum. And the eardrum vibrates. The vibration here is translated by the eardrum as well. Okay. Now we move on to the middle ear. If you look at the middle ear, that it has got 3 bones, tiny bones there, and the pressure at this point is amplified 25 times before it feeds into cochlear. So it's a kind of an amplifier, but its frequency response is roughly flat. It doesn't tune, it's not a selective. It is just roughly a flat bandpass filter. It's still a bandpass filter, but a very broad bandpass filter. Because many of you are electrical engineers, I'm using that terminology. So it does the impedance matching to make sure the small variation here is given the amplified and given 25 times more than the pressure here at that point. And then we move on to the next part, which is the cochlear, which is the inner ear. It's a very important part. That's the spectrum analyzer. I'll spend a bit more time here. So we looked at the outer ear, we looked at the middle ear, now we come to the inner ear. Inner ear is actually, it's called the cochlear, and it's just the actual signal processing, real signal processing. It's like snail. it's 3.5 centimeter, the length of it, and it has got 2.5 turns. And if you uncoil them, it looks like this picture. If you uncoil them, so if you don't uncoil them, it will be this picture. Okay, so if you uncoil them, what will you see? So as I said to you, this is the auditory canal, this is the eardrum vibration, and that vibration is transmitted by that, and then this is the stay piece. So the cochlea has got 3 parts. You can see that on the top end of it is one chamber, another part, another chamber. So this is fluids here. And here is also fluid there in cochlea. And fluid is here. The blue one is fluid and fluid here. And then between those fluid, there is a membrane, which is this brown one, which is called the basilar membrane. That membrane is frequency sensitive. You can see that membrane at that point is sensitive to 20 kilohertz. And at that point, it's sensitive to 200 hertz, or here 20 hertz. So you can see at that point, the membrane is 20 kilohertz, sensitive to, and here is 20 hertz. And this membrane does not finish up to the end because the pressure between here and here has to balance. Therefore, there's a hole there, which is called helicotroma. So through that, the fluid flow. So if this moves, this will move at the same frequency as this one. And that sets up the pressure waveform setup, and that pushes here, and this is small membrane that comes out, and when this moves this direction, this will move this direction, and that's how it is being set up. Because this membrane is frequency sensitive, if you give a frequency of 1 kilohertz, say if this moves at 1 kilohertz, wherever a position 1 kilohertz, you will see the membrane is displaced a little bit. So here is flat, and that position, say for example, 1 kilohertz, the membrane is displaced. So if you give 2 frequencies, I'll show you the next item, it will be displaced in 2 places. And the movement is in the nanometers, very small. And I'll explain that for a minute. So far, all I have said that to you, that Cochlear is a spectrum analyzer. There is a membrane called basilar membrane, which is a frequency sensitive membrane, which is separated by 2 sets of fluids. Now the membrane, when we go back here, the membrane, I have drawn a straight line here, but it's not a straight line. If you look at the membrane, it is like a trapezium. The basal end is here, that's at x equals 0. That is called apical end, that's x equals 3.5 centimeters. I told you earlier, it's 3.5 centimeters. So what happened now, if you disturb this at a frequency, if eardrum is vibrating at a particular frequency, you will find the fluid waveform travels up to the point where that particular frequency is here. So you can see that this is very small, this is wider. And the relationship, the frequency relationship is given by this equation. That has been measured by Beckerstein back in 1940s, that this is a logarithmic scale. X changes in distance. When X is changing, you see the frequency changes as well. So if you put X equals 0, you will get roughly 20 kilohertz. This is a constant factor. You can make it 22 if you want. So this will be 20 kilohertz. And then if you put X is equal to 3.5, you'll end up about 70 hertz at that point. That's 70 hertz. So different value of X will give you different frequency positions here. And when the wave travels, and when it sees a position where the frequency of the wave and the resonant frequency of this membrane is same, the pressure balances and the wave will not travel any further. And basically it absorbs the energy there. And there are different ways of explaining that. I mean, and a hydraulic engineer will explain differently. An electrical engineer explains differently. So all you need to know at this stage is the membrane is like a trapezium, and it's very, very stiff here, and it's a bit flexible there. and we have to model this membrane. That's the idea of this talk. So how do you see basilar membrane as a filter band? So let's look at the basilar membrane here. So low frequency, if I now give a low frequency at the eardrum, 100 hertz, the signal will travel along this, and wherever 100 hertz is around at this point, apical point, that where you will get the deflection of the membrane. If I give 1000 hertz, it will be somewhere at the middle part, you'll see the deflection. If I have 10,000 hertz, you will see a deflection at that point. And if you give all three of them, like combination of 100 and 1000 and 10, then you will get deflection there, you get deflection here, you'll get deflection there. There will be three places, there will be deflections. So we can actually see these as, model them as bandpass filters. We could say, right, the membrane acts like a bandpass filter, because when you give 100 hertz, it only oscillates there. So I need a bandpass filter there, and another bandpass filter, another one here, another one here. So we can take the membrane and model it as many bandpass filters. How many bandpass filters? We don't know. As many you want. Depends on the applications. Depends on the spectrum you want to analyze. And not only the bandpass filter bandwidth also different. You need, and cochlear signal processing, if you do measurements, you will see that the bandwidths are different at the different positions. So I'm going to show you a cochlear animation before I go into models. These are just fundamental of auditory modeling. So this animation is done by Howard Hughes Medical Institute, and I play that. It will take about one and a half minutes. So you can watch it, and it shows you, if there's multiple signal, how the membrane moves. Okay, let me get this animation going. Okay, it starts. So cochlea is uncoiled now. They're going to show that uncoiling the cochlea. And that's the basilar membrane, trapezium. Single tone, another tone, tone, tones. So that gives you an idea of, you can imagine how human cochlea, actually the membrane moves. And the important part is all these movements have to be censored by hair cells, and the information need to be fed to the brain. I'll come back to that part later. So at the moment, we are considering only the basilar membrane and how we model them. So models of the cochlea. So that's the next part. Now, this, I have done it in a way that, assuming that there are undergraduate students, so therefore I've kind of went in the basic analysis of circuit theory based. So have a look at it, and then you can ask me questions. So what we are doing is that we take the basilar membrane, we take a small section of the basilar membrane. So I'm dividing the basilar membrane with a width of delta x. So I can have as many sections I want. If I want 128 section, I divide the 3.5 by 128. If I want 2000 section, I divide by 2000. So that's how you find the delta x. Now, each small section of the membrane has got a mass. So membrane mass is an inductor, right? And it has got compliance as a capacitor, and it has got membrane losses. There's a resistor. That's in the electrical term. Or mechanical engineers will see it as a mass, a spring action, and a damper. Same thing. But as I explained to you earlier, the membrane, on top of the membrane, there's fluid, two areas of fluid there. So there's fluid mass as well. So the fluid mass is there. So one small section can be represented by an inductor and of the fluid and then resistor, inductor, and a capacitor. And then, so if you take the next section, that's coupled to the next one, same thing. So I have this one connected there. That's the first section, second section here, and third section, and so on. And then the last section is this one, nth section, section N. I've got N sections, and could be any value. And as I mentioned to you at the end, the basilar membrane does not touch on the fine. If you draw the cochlear, there's a hole there because the pressure has to balance. So that's fluid mass. So that's called helicotrauma. That area is called helicotrauma. So there's a large inductor, heavy mass has to be loaded there. That's the loading effect, actually. Those who are interested in understanding this further, you can actually do, those who are electrical circuit people, you can do a circuit analysis and solve them on a computer. All these values can be estimated. They are all measured values available. You need to do some sort of estimations. Measured values are available in terms of damping coefficients and stiffness. You can convert them, and then you can actually do circuit analysis. That's one way of doing it. Second one is you can do some sort of approximation. When you do the approximation, then you could say you can decouple. When you are looking at one section, you can decouple the other sections, you know. And there are ways of doing that, which I have done. There are papers published as well. So let's go and see how do we analyze this further. So we take one section of the basilar membrane, and we write the transfer function for this. Transfer function is this way. This is output. This is the input. This is the pressure input, which is proportional to voltage. This is the pressure output. And then, and there is membrane displacement is at the output of the capacitor. That is called the membrane displacement. So we can do the transfer function in S domain. And then when you're implementing it, you can just then do it on Z domain. So V output over V input, if you write a simple equation, you will find there's a low pass filter. You will find there's a resonant pole filter, and then you'll have resonant zero. This is complex pole, this is complex zeros, and you will have a real zero there for low pass filter. That's for all of them. And these values, by varying this value, this value, this value, and this value, you can actually, and also this value, you can actually design the system. Now, if you write the transfer function for the membrane displacement, that is that over that in terms of S domain, right? Remember, if you do that, you will get that one. You can see this is already included in the big one, in the pressure transfer function. It's already there. So when you implement this as a filter section, you will have input, and you will have a low pass filter, you will have a resonant filter that, you will have a notch filter, that's this one. And this displacement output, you take it before the notch filter. Output, that's the displacement output. And this output goes to the next section of the basilar membrane. Now, if you plot these characteristics for one particular frequency, you can see the resonant filter gives you a peak, and the resonant zero will give you a dip. The resonant zero is normally, this frequency is the previous resonant frequency, so that the previous resonant will not travel any further. This will take it away. So that's the clever trick that you have to use. And then this is the low pass filter will make sure that it has got a steep roll off. So that's a very simple system implementation, and undergraduate students can do them. You can try them out. If you have this system now, we want to, if you translate this transfer function into discrete model using any transformation, whether you want to do bilinear or whether you want impulse invariant transformation, it's fine. You will get these equations. And you can find these coefficients as well. All these coefficients values, these are filter coefficients. You can find out these values. So this will be a digital filter implementation. That's the section 1, section 2, last section. Section 1, the resonant frequency could be, we could implement something like 20 kilohertz, 16 kilohertz, it doesn't matter. This will be 50 hertz, 70 hertz, whichever. And you can then cascade those filters. When you cascade them, you got a transmission line type model. So you get filter 1, filter 2, filter 3, filter 4, filter N, and then this one. This one in the transformation, in the circuit theory, you need to have them, but in the S domain, we have transferred them back. So you don't need to worry about it. So that's your filter, actually. So what does that mean? Now we have modeled it. Let's look at some of the characteristics of it. If the model is correct. So we will have an input at the eardrum. Let's leave the middle ear for the moment and the outer ear for the moment. Let's say the input goes in here. We have got a filter 1, which is at a high frequency filter and low frequency filter. Yeah. Apical end means on the other end, that's the right hand side. It's a low frequency filter. So the signal traveling through will travel through filter 1 and travel through filter 3 and so on up to the end. And it sees it's, so if this frequency at if this frequency 1 kilohertz, so there will be one particular filter at 1 kilohertz. So signal will travel up to the 1 kilohertz, and here you will see a deflection, and then it won't travel any further. That's exactly, so that's what I'm going to demonstrate to you now. So what I'm going to demonstrate to you is this. If I now give a signal of 3 kilohertz, these are filter number, filter 1, 2, 3. So this is filter 1, 2, 3, 4. I have got 128 filters. I'm representing the Cochlear with 128 filters. And I'm giving a signal at 3 kilohertz, and it's traveling along this line and sees a 3 kilohertz filter somewhere. At that point, it will give a peak. And that there will be no more energy travel. And if you keep plotting every 10 milliseconds or 20 milliseconds on top of each other, you'll get an envelope like that. That's what you have. Now, as you know, at this point, the pressure is very high because you are really pushing in the cochlear. As the pressure wave travels, as it comes to the point of resonance, the pressure difference has to be 0. So you can see I plotted the pressure wave here, and pressure is, I'm normalized to 1, and pressure decreases, and this is also filter number, exactly same as that. At that point, the pressure is 0. It doesn't travel any further. So pressure is 0, so it has lost all the energy. There's no more energy travel. Now, if you give an impulse at this point and look at the impulse response at one of the filter and take the Fourier transform of it, and you can see its frequency characteristics. This is frequency, this is magnitude. You already know these ones. And it's a very sharp filter. This sort of a roll off of that, something like 250 dB per octave, you won't get this one in a normal filters. Only cascaded filters can provide them. That's how the Cochlear is able to separate two frequencies really well by having this sort of a cascading effect. Can I just stop at this point and ask you, am I going too fast, or are you able to follow? I should have asked this question before.
Yes, sir, you should be able to follow. Yeah, thanks.
Okay, follow. Thank you. Okay, so I've explained to you how the membrane displacement is membrane movement. So it's all membrane movement is all happening. If you look at Cochlear, so what we have learned is that this membrane, we now know how to model them as filters. We can model them as 128 filters, 1,000 filters, as depends on the application. Now, this movement have to be picked up by something. So what I do is now, I take a cross section of this membrane, and I just show a diagram here. If you look at this diagram, this is the cross section. That's your membrane. In this diagram, I've got fluids there. That is that part. And this part, sorry, this part is this one. What I have not shown you here is this one. It's a very small area. It runs through across the membrane. This is where the hair cells are sitting on top of the membrane. So if I take a cross section, I only show this part only now. That's what I'm showing here. You can see this is the basilar membrane, cross section, one small cut I did. And on that, there is something sitting here, right? Exactly here. What they call is a tectorial membrane, plus it has got hair cells. This is one set of hair cells. These are three sets of hair cells. So they're the one who actually pick up the movement of the membrane. So let's go to the next page. So what happened is that along this membrane, there are 30,000 hair cells sitting there, picking up the movement of the membrane. That sort of information being transferred. So there are 30,000 hair cells there. There's one row of inner hair cells, that is called the inner hair cells. And then 3 rows of outer hair cells. If you look at the block diagram here, basilar membrane output, the inner hair cells send the signals through afferent fibers to the auditory system to process. So inner hair cells are responsible for picking up the movement of the basilar membrane. And then through the efferent fibers, outer hair cell control the basilar membrane. And I'll come back to that for adaptation later on. So for the moment, just concentrate on the inner hair cells. So we leave out this for the moment. Inner hair cell, what do they do actually? Okay, when this membrane moves upwards, there is liquid around here. They flow along this path. They flow along this part and they bend this hair. So the hair, the next slide shows you. Here is this is the hair cells. And when the fluid flow, this bends the hair. Bending the hair is equal to modulating a current through this. So if we go back to the diagram again, so as soon as it bends, it just sends a signal through this one. This is the nerve. So that's exactly the output here. Nerve pulses being sent through this, modulating a particular current. So what happened, the membrane moves upwards and then comes down, then move upwards and come down, right? So which is same as hair cell bending and then coming back straight, bending and coming back straight. So which is going only in one direction. So if we are modeling it, we will say going in one direction is a half wave rectification, and bending and then coming back is charging a capacitor and discharging. So you can actually model the hair cell by basically having a half wave rectifier with a simple RC capacitor charging and discharging method. That simply works without any problem. There are complicated models available, and they don't improve anything better than this one. If you average all the complicated models, they ended up like this model. So inner hair cell models is responsible to transmit the basilar membrane movement to the auditory system, to the brain. So one more thing that I need to explain before I show some results for you. Let's go back to this one. Because the you see the hair cells are sitting. Let me go back to the diagram, it's a bit harder. This is one section. If you take the next section also, it would have same thing. So these hairs, there's fluid here. So there's a fluid coupling happening in between. So basilar membrane movement is happening, but then the fluid also coupling them. The fluid here, not the fluid that we learned here, not that one. This is the different part of the subspectorial space fluid. So what happened there is, because of that coupling, there is some sort of a differentiation happening, a high pass filter effect. So we need to actually introduce a high pass filter effect before you introduce the hair cell model. Because we haven't introduced hair cell model, we introduced them as this one. Cochlear model, we introduced them as that one. But the fluid coupling, we haven't done it. So fluid coupling, what you need to do some sort of a spatial differentiation between filter 1 and filter 2. And that's what you feed in here. Filter 2 and filter 3, that's what you feed in there. What does that do? Well, let me explain to you that in an example. So I give a signal to my filters here. I give a 1 kilohertz signal here at that point, 1 kilohertz signal here. It travels along and sees some filter at 1 kilohertz, it will cause a vibration and then it goes 0. That's what here. So you can see if I don't do spatial differentiation, if I just give the membrane, every part of the membrane vibrates. This vibrates longer, but this vibrates a lot. That shouldn't happen. The fluid coupling makes sure that does not happen. So one cannot push up itself too high. So by introducing spatial differentiation, a new technique, we actually came up with that technique. By introducing that, you can actually make this really flat. And if you do another spatial differentiation, it will be further flat. You can do double spatial differentiation on this. You differentiate this and then do differentiate before you feed in there. So that's why I've introduced a high pass effect, filter effect of spatial differentiation there, which actually makes sure that this is actually flattened and you are only interested in this part. So there are three parts in the cochlear model when you are modeling. One is, we will leave out the middle ear and outer ear for the moment. That's only for simplicity, I explained to you. We need to have the cascaded filters first, and then we need to have spatial differentiation. And then we have inner ear models, sorry, inner hair cell models. And the signals are electrical signals. We're going to look at how they look like. So far, we looked at that point. We haven't looked at that point yet. That's the next slide. Oh, next slide, sorry. I'll come back to that next one. So most of your front end, most of your speech application or machine learning application, your filter banks are not cascaded filters. They are all parallel filters like this. Filters are in parallel, one, the next one, next one. They're not connected to each other. And it's easy and simple and very easy to implement. So almost all the people will tend to use that one. They don't use this cascaded because it's too hard. But if you look at the cochlear characteristics, cascaded filter, the only filter is able to provide this sort of 150 dB per octave roll off. These filters will not able to provide them. They will provide them selectivity, but they won't provide them. So when you use these filters for frequencies, if you want to resolve two frequencies, you will struggle with this one. You would find it easier this way. So with machine learning, I think we could just bring this in pretty easily now, but we can still do this one as well with machine learning. So we're doing both of them at the moment. Now let's go back to the next one. So you can use this one or this one, but this one actually explain how the Cochlear does it. This one is like a simplified version of this one as a front end. Now I'm going to show you the output. So I'm going to give an input, 3 sine wave, 3.2, 1 kilohertz, 300 hertz at that point, or that point doesn't matter. And I'm going to look at the output here, spatially differentiated output, and then I'm going to look at the output here. So if I give the output there, I'll see at 3 places, membrane, this is the displacement, this is the filter numbers. three places the membrane vibrates. You can see that. Our hair cell model picks up the vibration. Hair cell model basically remove this part, remove this part, remove this part, because it's a half-wave rectification and charging and discharging. So it'll just take the envelope roughly, envelope. And if you these are the three signals being sent through the auditory fibers, and that's what the signal is. That's at one point. There's another point. There's another point. Okay. So that's so far the cochlea, where the filter characteristics are fixed. We have not changed the characteristics at all. But in reality, human cochlea characteristic changes, constantly changing. If you ask me every how many milliseconds, very hard to know, but at least every 5 milliseconds it's changing. How does it change? Where does the signal come from? That is the outer hair cells. Remember I showed you earlier, is responsible for that. So human auditory system can process a vast range of sounds spanning some 12 orders of magnitude in input pressure intensity. So we have, what I have explained so far is called passive cochlea. We only have frequencies are fixed resonance Q values or bandwidths. They don't change. But in reality, it's adaptive. It does change. So what happened is, while you are having a conversation with somebody, you heard a small pin drop, something dropped, very low sound. Within a millisecond, you're able to hear that. So cochlea, as soon as it's received a signal, it increases its gain and the bandwidth, changes the bandwidth, and boosts the signal strength to see whether it's a useful signal or unwanted signal. So it does adaptation. So there's enough evidence to show. Look at this picture. This is the basilar membrane, and this color is showing the passive cochlea. It's a fixed characteristic. If everything in passive mode, it may not pick up that sound, small sound at all. And as soon as it's pick up a small sound, if you hear a small sound, the outer hair cells exert some force. So outer hair cell from auditory processing through the fibers, signal goes into the membrane. Whether it's a membrane or whether it's in the tectorial membrane, we don't need to go through them now, and exert a force, and it provides a amplification. And that amplification is able to pick up that sound. So that is called adaptive gain. So you can see that there are enough evidence to demonstrate that it's not always on passive mode, it's in active mode. So if it's a 20 dB signal, very low, less than 20 dB even, this only this actual measurement. So they were only able to measure up to 20 dB. 20 dB, very sharp characteristics. You can see that. Bandwidth is small. It is increasing its gain and smaller bandwidth. And when you give an input signal higher dB, it's broader. The Q changes is broader. They're not sharper. Right? So the cochlear filters have to adapt its bandwidth and its gain constantly. So we need to include that one. So that's the next part of it. So how do we do that? So we know that from physiology that tectorial membrane was responsible for that as well. It's a resonant mechanism as well. And there is some sort of energy being fed back. So earlier we had the model like that. Now we will have tectorial membrane. It's a resonant structure, and they're coupled with the spring action and this one. And if you model this one, earlier you only had that part. Now you got to include this one, which is that, plus that one, which is that, plus there's energy coming in, a source of energy that. So you end up with new model now. if you want the adaptive model. I mean, the reason I'm giving all this circuit is those who are electrical engineers may be interested in seeing this one. Your circuit transmission line model changes now. Earlier, this was connected here. Now it is through this one. So you can now write transfer function for this one, which is not difficult. When you understand the first one, it's not difficult. And then we can actually change this signal, the amount of voltage that we feed in. We can change this one, and instead of that, we could this gain we can include them into the active part of the filter. That means we can adjust the filter bandwidth. So how we have done this one in the active transmission line model? This is our model. Remember, this is our model one: basal end, apical end, tunable end. This is our inner hair cell output. We take the inner hair cell output, keep monitoring, and we do get feedback from the outer hair cell. And using that feedback, then we will feed and change the filter characteristics. So if you do this every 5 milliseconds, for example, or every 2 milliseconds, it doesn't matter. You decide what you want to do, and if you make changes, and so if I get a signal now, it will only change for the next 5 milliseconds because it has to do all these calculations and do that change. So you change the characteristics. So how does it help you? So you can see here a passive cochlea is in blue color. I mean, characteristics are not changed. So if I give a signal of small amplitude and a high amplitude, passive cochlea is the blue one, and the blue one is here. It just sees as a small amplitude. You could miss it even that. I kind of made it bigger so that you can see it. If you have an active model, it will boost that energy so that you don't miss that signal. Very important in like speech application, in spoofing application, for somebody is trying to mimic you, recording your voice. So we need to extract the high frequency information, but they have very low amplitude. Very hard to get with the normal filter bank. So you need to have adaptive filter bank who can actually pick up, and I'll show you in a second. So the adaptive model should be level dependent, sharp auditory tuning curve, and fast adaptation. And that's exactly what we have implemented. And if you implement that, and if you give it to a speech signal, and this is passive cochlea, this active cochlea, this is kind of a spectrogram, it will show you that it's able to pick up quite a lot of information in the high frequency end, whereas passive constant Q filters fail to do that, you know. So that's all the models of the cochlea now. So I think the last part, I don't want to delay, integration of cochlear models with machine learning. So how does that help you? So we know that we have to tune this filter, important. So we could use, I mean, this is a more detailed version, but you could have one DNN making the decision. Using the decision information, you feed the error back to another DNN, control these filters until you get the thing right. So we could implement these filters also part of your DNN structure, deep neural network. DNN stands for deep neural network structure. So one example that we have implemented, we didn't implement it for but a cascaded filter because it's too early to do that. We need to learn it from the parallel filter first before we implement. Here's one model that we have implemented, integrating auditory models, parallel filter bank with the DNN. So we have got parallel filter banks here. Instead of adapting this filter, we decided, no, we will leave that. We will put in, there's enough evidence in Cochlear, there's a second filter available, which is the tectorial membrane filter. So we have second filters here. And we will change the characteristic of these filters. We will keep this fixed. We will change these ones. But these are all FIR filters. so that you can actually use all machine learning algorithm, because they are all FIR filters. In previous versions, all of them are IAR filters. So we will, after spatial differentiation, we will get the signal, we'll calculate the energy. We will say, okay, if the energy is high, we need to change the Q to low value. If energy is minimum, we're going to go high value Q. And if energy is in between, we set the Q. So we have got a predetermined thing based on various characteristics. We don't need that. We can integrate that here as well. But we want to go step by step. So the output of this, we do the feature extraction. Then we use the DNN. It's a massive DNN network. I didn't want to go into detail. We get the, we look at the output decision, and we look the error. We propagate the error for this one, and we propagate the same error back through this network. This is also another network. And that network actually tells us what changes you have to do to this Q value that we have estimated in order to get the right decision. So we get that Q, and that Q will control these filters. So you may suddenly find out of 128 filters, for example, only 20 filters characteristics may be changed, or maybe only the high frequency characteristics are being changed, not the low frequency and are not changed, or all of them are changing. So it depends on amount of data that you have. You train the network, and then you do that. So eventually we want to have this. All these will be integrated through this system in a parallel filter bank, because currently a lot of things are parallel filter banks. So we want to make sure the machine learning technique is integrated in the parallel filter bank. And this is adaptive, continuously adaptive every 5 milliseconds. It is adaptive. And then we move on to the cascaded filters. So that's the DNA integration. I mean, this is one way of integrating. I'm not saying this is the way of doing. You could do other ways as well. So what's the future trend? The future trend would be, remember that we have got 2 years. So it's binaural. So once we have done one of them, so for example, if we do the channel 1, we have got this part working, we would have the second one implemented. And then we need to learn how the human able to separate things and use that knowledge. And when you do binaural, the characteristics of this cochlea and the characteristics of this cochlea at any one time will be different cues, different values, because the signals coming through different channels. So they got to operate separately. So we are working on this one for selective hearing. So we use the machine to selective hearing is when there are many people and you want to only select a particular person, and the machine wants to hear only one person's voice. How do you do that? That's the application of this one. So that currently we've got funding to work on that. So this part of the work is almost there with the parallel filter bank. We haven't done the, so it's important to understand the transmission line model if you ever want to work on this one and get that model implemented. Through that you have a full understanding, and then you can move on to the next one. So where would you use them? Once we have got all the feedback mechanism, you can use this in deep learning integration once you have in the state-of-the-art speech processing systems. So because the current speech processing system have got machine learning built in, but the front end is not adaptive. And they do have recently in image processing, they are bringing in adaptation. I can see that. But most application would be in the parallel filter bank is for cochlear implants. Once you have got the adaptation and machine learning into the behind the ear processor, then you can adapt that, you can program that for a particular person, and it is adaptable as well based on the, using the artificial machine learning techniques. It can adapt itself, depends on the environment. So that would be the next step once this is working. That's all I want to give you. I hope I've given you some background on cochlear models and also machine learning integration. I only showed you one. I mean, we can run one session on machine learning only, but without having the fundamentals on that, it'd be harder. So thank you. If you have any question, I'll unshare it and you can,
Yeah, thank you, sir, for the interesting talk. So the Q&A session, so you can ask the questions.
Thank you very much, Professor Ambikairajah, for a very interesting talk. Actually, I'm mainly working in the image and video processing area. So I have learned but basically the human visual system, but this is a very nice talk on the our hearing system. So basically I have a few questions. So the one is that in the filter banks you have mentioned, and so in this case, the bandwidth, are they uniform or basically is it non-uniform bandwidths are incorporated?
Yeah, they're not non-uniform bandwidth because the bandwidth, the Q value, quality factor value varies from, if you look at the cochlear measurements, they shows only for a few frequencies they have given Q value actually measured on, on human cochlea. So values varies from something like at the low frequency end around 2 quality factor about 2 to high frequency end about 15, 12 in that range. There's no hard and fast rule as, but is it normally in that range? And sometimes it's useful for us to have a high Q for selectivity, but in the transmission line model, there's one thing I haven't showed you. It's important that a signal starting from the eardrum through the cochlea need to travel to the end. So if you have a 100 hertz traveling, it needs to travel within 10 milliseconds. The measurement shows that cochlear travel time is about 10 milliseconds. So if you are designing filters with a very high Q, then the group delay will be very high and it may not travel in 10 milliseconds. That problem will be there. But if you do it with parallel filter banks, you could avoid that, So, to answer your question, Q values are in the range of 2 to 12, 3 to 14, things like that. You can use it.
Yeah. And in that case, because in the basically in the parallel filter bank implementation, I have seen basically in the uniform filter banks, we can use the cosine modulated or modified DFT such as, but in this case, how the filter banks have been developed or designed using optimization techniques? So
no, I didn't use optimizing. So what I did is, can I just share it again? I just quickly show you. I'll keep my slides. So what I did here is, I just go to the filters bank. Okay, just for example. So sorry, I had the equation here. So you see, this is the fundamental equation. So we have the Q value. If you know the Q, so Q I said it varies from 2. So let's say 2.5 to, this is for low frequency, to high frequency 40. Let's say. So the bandwidth is equal to center frequency F divided by the Q. So once you select this one, we have the bandwidth as well. Then you can use any of the transformation technique to get the digital filter, which is this equation. So once you have the analog filters, then you can use the digital filter transformation to get all these coefficients. So is that clear? Is that what you're asking? Okay, all right, okay. So that's how we did it. Yeah.
Okay.
You can do in the FFT domain, like the way the MEL filters and others do in the FFT domain, but variations will be very difficult. You just keep them fixed, You can use FFT filter. You take an FFT of the signal and then.
Okay, sorry. There has been a disturbance.
No problem at all.
Okay. And also what I think is that actually, this what I feel is that the circuit model actually, it's a very extremely simple and basically it's a very nice model, and So it captures all the actual dynamics of the
Yeah.
ear and everything. So what has been the exact motivation to go for the deep learning based controllers? Because this is a very nice model for a circuit designer.
The reason was, I mean, it's a good question you're asking. I mean, it's not easy to answer the question, but I'll answer. Let me get back to it. So the reason is this. So when you have this model, when this is our excuse me, basic filter model, we could have without deep learning, just simple filter model. But the difficulty is then we want to know if you have fixed model here, you feed input, you have a deep learning technique here for classify, it classifies the output. Whatever output is the output, we can't. But if we can train, while we are training this one, if we can also use that knowledge when you're training it, use the knowledge to change these characteristics, then it could be much better system. Then you're using both world of it rather than independently. At the moment, it's kind of independent. You keep the front end fixed, you know. And so I think to make it adaptive, we need to tune this one based on that.
Okay, thank you so much for actually. It's a very nice talk, and yeah, I learned a lot actually. Thanks so much.
Any other questions?
Hi, everyone. Hi, Professor Ambikairajah. This is Chamit.
Good to see you. Good to see you there.
Happy New Year to you and to everyone.
Happy New Year too. You're not in Sri Lanka, are you?
No, Professor Ambikairajah, I'm just in Brisbane.
Okay.
Yeah, it's thanks for the very informative and nice talk. I just had a question from a systems perspective. In terms of implementations of the deep learning, the machine learning part, should it be, so is it like in-system training required? Is the model, so it's not like the model is pre-trained, you find the optimum weights, and so it's both the training and inference has to happen in system.
Yes. It's not fixed, no.
Okay. So
it is in a testing. If you can make it fixed, that's possible. Okay. You know, you can use the feedback to modify them, but then you know
it's not fully adaptive.
It's not fully adaptive. That's what will happen. And the adaptation is important because of the variation in the sound. The amount it varies is you want to continuously track. You know, and we want to change the filter characteristics. I mean, people do track them continuously by keeping the front end fixed and looking at in time. But we want to change the front end as well, adaptively change it, and also in time as well. So I think system implement wise, it won't be adaptive. We are now in a position where this one is almost done. We're kind of submitting a paper at this stage now. We've got a pretty good results. We applied for spoofing detection task, which is a major task actually, a lot of data there. And we can do significant improvement. We can see that using of the adaptive methods, you know, compared to the non-adaptive. But we need to evaluate this in various ways, because we have got to demonstrate the adaptation is the improvement is not due to the fantastic backend you have. It is due to the adaptation. So we got to try out other applications as well. So it's a bit early stage, Shamit, for us to say yes, this is the best model. You know.
Okay, thank you.
Okay. Any other questions?
Thank you, Prof. Ambikairajah, for giving us a very clear talk. I'm through here.
Through, yes.
I have a question. Like in one of the slides, you have the with the dBs the amplification, So basically, you have mentioned that when
Sorry.
there's faint sound, there's a big amplification.
Yeah.
So
Yes, yes.
yeah, is there any constraint on the duration of the sound? So am I clear with the question?
Yeah, no, you have. I'm trying to see, because the signal needs to be there for some time. I don't know how long. That's why we are doing the question is that earlier, should we do the adaptation every 5 milliseconds or 2 milliseconds or 1 millisecond?
Yeah.
We don't know that.
Yeah. Yes.
Because there's the adaptation part, how long the sound has to be present, the knowledge is not available to us. No measurements available.
Right. Yeah.
People know it is adapting. They have done measurements giving a low frequency, low amplitude signal, and its characteristic changes. They've seen that.
Yeah.
But the duration of it, how long, whether it's a couple of, it's be in the order of millisecond, but whether it's 5 or 2 or 3 long, it should be there, we don't know. So our understanding is that within 5 milliseconds, we will look at and we'll do the adaptation. And next frame comes in, if there's no change, it'll go back to the normal. You with me? So we are using kind of a 5 millisecond as our window length for adaptation.
Yeah, okay. Yeah.
We are assuming the signal is going to be there more than 5 milliseconds, you know?
Right, yeah.
So it's not, no, it's a good question, Thiruvan, but don't have the answer.
Right.
I mean, all these are nowadays, not many people do real-time measurements in Cochlear. I think the trend moved away a little bit. And so those days they tend to do and they publish them. Nowadays it's not really, so we don't have that information.
Right.
But you know, could be there somewhere, we haven't looked at it, but it's hard to know how long the signal to be present to do the adaptation. Yeah, it's a good question.
Yeah. Thank you.
So any other questions? Thank you. So I kindly invite Dr. Samir Edisuriya, Chair IEEE Sri Lanka Section Signal Processing Society Chapter, to deliver a vote of thanks.
Good evening to everyone. And so it's a great pleasure to have such a nice talk from the Professor Eliathamby Ambikairajah. And so actually the Signal Processing Society Sri Lankan chapter we have established a few months ago, and this is the first ever technical talk, and the first name came to my mind is Professor Ambikairajah. And also, so I mentioned this to Ahilan because at Sri Lanka we have 2 student branch chapters, one at the University of Morato and the other at the University of Jaffna. So as a person at the University of Morato, I wanted to start with the University of Jaffna and give the opportunity to them and start the first task and the first technical talk. And so this is the first time I have listened to a lecture of Professor Ambikairajah, even though I have worked with Dr. Chamit Vijayanayake, and also we have co-authored a few papers with the Namalka. And so I take this opportunity to actually thank you very much. And I know it's very late night now in Australia, and thank you for your time. And also this is a very great lecture, and it shows that why you are not excellent in DSP, but as well as education as well. Thank you very much, sir. It's a great honor to have your presence as the first talk in our society chapter. And also I would take this opportunity to thank the Dr. Ahilan Kanakasundaram for organizing this event, and also all the members of the student branch chapter at the University of Jaffna. And also I would like to thank all the members attended, and also thank you, Chamit, again attending from you also from late night. And yeah, thank you all the members who have attended, and have a good night to everyone.
Thank you so much, and thanks for attending it. And I was just to mention to you, I was unwell until today. This morning I was thinking what I was going to do, because as you know, there's all sort of trouble in Sydney. It's nothing related to COVID. Everybody has flu at the moment here, not COVID at all, but just flu. And I had one of them as well. So it was just hard, but it was all good. At the end, it worked out. So it's good. Thank you so much.
We really appreciate,
and I wish you all a good success with your future talk. And if there's anything that we can do, please let us know. Okay.
Thank you
so much.
Thanks.
All the best. Bye-bye then. Bye.
All the best.